Good afternoon, everybody. I'm Amir, a member of the International Space Station Archaeological project. This project led by Walsh from Chapman University of California and Alice Gorman from Flinders University of South Australia. Our project established in 2015 to study how material culture is used in creation and maintenance of a unique space society. As it's not possible to conduct archaeological fieldwork on the ISS due to prohibitive cost and crew privacy, NASA has provided data in form of the photographic archive and the inventory management system IMS database, which catalogs all objects sent to the station. In this talk, I discuss the challenges in studying photographic collection of this kind, using the example of absence or presence of astronauts in ISS modules. I also discuss how data science techniques have repurposed IMS legacy data using Ziplock bag case studies. Ziplock bag is an artifact type found on the ISS since its inception. ISSAP is the first archaeological study of a human habitation in space. It's an ARC discovery project, and it's joint collaboration of two universities and NASA, Flinders University of South Australia and Chapman University, Wilson College of Art, Humanities and Social Sciences, and Chapman University Machine Learning and Assistive Technology Lab. As I have mentioned, we have two main data sources, which one is NASA archives with more than 7,000 images, and a legacy database called Inventory Management System, for short, IMS. What are the aims of ISSAP? To investigate human engagement with material culture in space, to identify the meanings associated with the spaces astronauts inhabit and the objects they use, and also to identify how humans adapt to space technology, and the most important one, to evaluate future design of long duration space missions. What is the ISS? ISS is a huge modular laboratory which its size is equal to volume of a 5-bedroom house. It has more than 16 modules, 4 Russian modules, 9 American, 1 Japanese module, 1 European, and also 1 Canadian robot arm. The ISS orbits Earth at a height of approximately 400 kilometers, and also it takes 90 minutes for the ISS to make one complete turn around the Earth. It has 4 interfaces for cruise ships or resupply ships to be docked at the same time, and also its environment, it's a microgravity free fall environment. So basically the objects moving around in the station. Let me give you some more facts and figures about the ISS. ISS continuously occupied for 20 years in November 2020, and it operates until 2024. This is an extended operation time. It's international collaboration between 5 space agencies and 25 national governments. So far, over 240 human visitors traveled to ISS. Some of them were paying tourists, and the total construction and maintenance cost of ISS was 150 billion, and per year the space agencies spend 4 billion to maintain the ISS. The 60,000 is the cost of a crew per hour in the station. The first module of ISS was Zarya. It launched 1998, and also the first person arrived on ISS was William Shepard. He arrived November 2nd, 2000. So far, space agencies operated more than 42 assembly flights to deliver the ISS components and modules. And there is a record which is 665 days. This is the longest a person lived and worked in the ISS. How to conduct an archaeological investigation without fieldwork? The ISSAP method for doing this has 3 main phases. We use machine learning techniques for our large-scale image archive, and we use data science techniques for our legacy inventory management system database. And the result of recovery and analysis of IMS will be used for augmenting the machine learning result of our image archive, and then the data will be stored on a hybrid graph database. Let's see how we extract and record data in our graph database. In this slide, you can see a subgraph which is belonging to the image on bottom right. If you look at this image carefully, it's a simple image with few objects. And you can see a laptop is on top, a flag on bottom of the image, and few other objects in the hands of astronauts. If you compare this image with the top right image, you can feel the complexity. There are much more objects in the top right one. And obviously, its subgraph would be much more complex. And I wasn't able to show you the subgraph in this slide with the complexity of this image. Let me talk about our data model. We have more than 65 entities and the relationships among those entities. In this subgraph, you can see that image is one of the main entities. It's connected to the objects in the image and the crew members in the image, if any. And also we record the activity of the crew member, the one that he is involved in, and if it's associated with the object. Also, we record the view of the image. We record 2 locations for each object, the location of each object in the space module and the location of each object in the image. So let me go through an example for you. Let's talk about this laptop. This laptop is recorded in this node. This object node has these properties: description, it's laptop; category, it's electronics; type is computer, and only we can see one laptop in the image. Its location in the image, it's in the module named Kibo, it's the Japanese module. And the location is upper left and foreground. NASA has its own system for the directions. Forward, it's forward; backward, it's aft; and left, it's port; starboard is right. And in these properties, you can see the location of the laptop. It's on aft, top, port, and it's a tight object. The reason that we evaluate loose and tight, it's because of the environment of ISS. As I have mentioned in the earlier slides, the ISS environment, it's a free-fall environment, and objects are moving around. So the definition for a tight object is an object that held by somebody or attached to a wall. One of the main IMS tables is item table, which is connected to other tables of database, for example, item type, item location, and item status. Looking at all these tables and values, we have lots of missing data, like empty tables, null values in each table. And also, we can see values that are semantically equal, but they have been entered with different formats. So we have inconsistent formatting in IMS. Also, we have inaccurate data, such as Russian values for specifically designed columns for English values. And I can say space agencies did not maintain well the IMS, and the entities need to be identified and data need to be clean, organized, and analyzed. In this slide, I described what were the challenges that made us to develop a data scraper for scrapping NASA Johnson Center Flickr account, which contains more than 24,000 ISS images. The problem that we wanted to address was identifying each appearance of every individual and their locations in ISS. For doing that, module names and crew identities need to be identified. We have used machine learning techniques like image recognition and face recognition to addressing this problem. And The ISIS images, like the image that you can see on the center of this slide, have people at the foreground, and astronauts have covered part of the image pixels that machine learning algorithm use for training. So we have two data sets for machine learning. One is training data set that machine learning use it for learning, and then the other data set, which is the main data set that the machine learning extract knowledge from. Having people at the foreground reduce the accuracy of machine learning model, but this is not actually a big issue with a large training data set. The second challenge was the face recognition technique that we used that sometimes misidentified the Asian crew, and also it had low confidence rate for the side faces. So to overcome these issues, Web Scraper accesses the Flickr website, parses the content of the page, like image ID, the date of the image description, and in the image description, the module name and the astronauts' identities. This table summarizes different entities for Ziplock bag from acronym column of item table. You can see an example in red, which indicates a Ziplock bag of 12 by 12 inch in different tree formats. This is the case for this column, and it's the proof of lack of data validation for this table and the IMS database. The other problem that we had with this column, they have entered numeric values for the acronym column, which should contain acronym of an item name. Here we have a graph that indicates the items that need to be returned to Earth from ISS with three stages like early, standard, and priority. You can see Ziplocks among those items, and it's interesting, they have been entered by Ziplock without the bag keyword. And you can see the proportion of each item. And the most interesting part of this graph is the big chunk of light blue, which it indicates the blank records. So you can see we have lots of blank records. Mainly half of the graph, half of the items are, half of the records are blank. This table indicates an example of our data inspection for our Ziplock case study. In the header, you can see how we have inspected the Ziplock bag. We have learned that astronauts enter sometimes Ziplock bag, sometimes Ziplock without bag, and sometimes Ziplock as two zip and lock words. The first column indicates the tables, and second column indicates the columns that contain these words. So basically, according to these statistics, we can understand item is the main table, and the tree table has some invalid data, like Ziplock entries, which are alphabetic values for part number and serial number columns, which should contain only numeric values. As a summary and conclusion, we have faced many challenges working with multimedia datasets and a legacy database. We have developed AI tools for analysis of ISS images and IMS data, that the result of analysis can answer questions about patterns in people, objects, and spaces. The tools that we have developed have potential application to the analysis of other large social and historic multimedia datasets, such as the Farm Security Administration, Office of War Information Archive, and the digital collections of the National Institute of Standards and Technology, and also the Stanford Libraries collections. Our tools have potential applications to other remote or inaccessible areas datasets. These are some of ISSAP publications. I would like to appreciate and also acknowledge the support that we have received from NASA data expert team, and I'm ready for the questions. Thank you very much for listening.